this lecture, we will discuss Chapter 2, which deals with kinematics. Kinematics is basically the first topic that we'll hit that can be expanded on and will be expanded on throughout this course and the rest of the semester. The topics that we handle in this chapter today, they will be discussed in one way or another throughout the rest of the semester, and you'll see a lot of times it'll be referenced in some way, form, or fashion the later chapters. So it's crucial for everybody to get a decent understanding on what is going on and why things are being done throughout this chapter. So our formal study of physics begins with kinematics, which is defined as the study of motion without considering its causes. In order to understand motion, we first need to know where an object is. We define position as the location of an object at a particular time. In this chapter, we will only consider motion in one dimension, so we can think of position as a point on a number line. So basically, if we do not know where an object is, there is no way of us understanding exactly what we need to do with that object. So position is crucial. We need to know exactly where the object is to understand where we have to go, what we have to do with that object. So as far as displacement, it is defined as the change in position of an object. It is important to know for displacement specifically that we do not care how the object moved or what path it took to get there. We are only interested in where it started and where it stops. So for displacement, we have our first equation. We have delta x, which is that triangle. That's what the delta symbol is. Equals the x final. That's what the F represents. Minus the x naught. That's basically your initial x. So we have your final x minus your initial x. And that is your change in displacement. So for this, it also has a direction. So displacement can be positive or negative. And we'll understand in a little bit how we can get those negative values. So for figure 2.3, we have a teacher that goes from the left side of the board to the right side of the board. She starts at 1.5 meters, which is your x naught, and she goes to x final, which is 3.5. So we simply do 3.5 minus 1.5. And that gives us 2 meters in the positive direction. Pretty straightforward here. For this one, though, we have a passenger that moves from his seat to the back of the airplane. So he was somewhere in the front or in the middle of the airplane here. So his initial position, according to the airplane, is 6 meters, right? And he goes to a position that is now 2 meters. That's his final. So here we do 2 meters minus 6 meters. So his displacement here is negative 4 meters. So now here's where the difference is with distance. While yes, we have displacement, distance is the magnitude of displacement. So distance will only be the numerical value of displacement because distance does not have a direction. Distance traveled is the total length of the path traveled between 2 points. So the path taken does matter when we calculate distance traveled, and we'll see some examples in the next slide. So for here, we have a cyclist rides 3 kilometers west and then turns around and rides 2 kilometers east. What is her displacement? What distance does she ride? And what is the magnitude of her displacement? So here, for A, we are worried about her displacement. We are worried about where she started and where she ended. Remember, displacement does not matter on what path she took. So we do know that she went -3 or 3 kilometers to the west and then came back 2 kilometers east. So our displacement here is -1 kilometer. She's only 1 kilometer away from her initial position in the west direction. So here in the compass, as you see, west is in the negative direction. So that's why that negative gets tagged along with this answer. For B, we have distance. So we know that the distance she went in the first place, she went 3 kilometers to the west. Remember, distance does not have a direction. So we really are only worried about those 3 kilometers. There is no negative here. And then she went 2 kilometers east. Again, we don't care about the negative here, but it's positive anyway. So we have 3 plus 2, which gives us 5 kilometers. And then the magnitude of displacement, we could see from A that the numerical value here is just 1. So that is what the magnitude of displacement is, 1 kilometer here. All right. So for this diagram here, we are trying to find out what displacement and distance it is on each path. So for A, it's pretty straightforward. They started like around 0. They went to about, let's say, 7. So the displacement is positive 7. The distance traveled is 7 meters. That's what our units are here. For B, they started at 12 and went to, let's call that 7. So remember, for the equation, we do the final minus the initial. So here it would be 7 meters minus 12, which would give us 5 meters. That is what their displacement is. Now, distance is the magnitude of the displacement, the numerical value. So for distance, it would just be 5 meters. For C, they started at 2. They went to about 10, came back to about 8, and went to about, let's call that 11. So from 2 to 11, and 11 is the final, 2 is the initial here. So 11 minus 2, the displacement here is 9. 9 meters in the positive direction. Now the distance, however, it's 2 to 10, so that's about 10 minus 2 is 8 meters here. Then they traveled 2 meters this way, so that's 8 plus 2, that's 10, and 2 meters back to the other direction. So their total distance here is 12. So you see where there's a little difference there. And for D, they started at about 9, right? And they went all the way to about 3. So the final over here, they went 3 and then they went back to about 5. Let's call that 5. So 5 minus 9, that gives us negative 4. And for the distance, they went from 9 to 3. So that's 6. And they went back to 5. So that's about 2. So that's 8. 8 meters for the distance. So each one of these has a different distance. Displacement. A and B are pretty much straightforward. For C and D, there's a little bit of thought process I need to go into it, but you just have to remember distance. It does matter what path you took. Displacement does not. Displacement is just the initial and the final. All right, so that'll bring us to vectors. Why is there a difference between distance and displacement? Well, displacement is a vector and distance is a scalar. A scalar value has a size or magnitude, but no information about the direction. A vector has a size and a magnitude, or a magnitude and a direction. Sorry. So for vector examples, we have displacement, velocity, and force. For scalar examples, we have temperature, energy, and height. So these two are related. Scalar examples are just basically anything that just has a numerical value. So, the speed of a car, things like that, you just see the number. Like they said here, the temperature. Vectors are a little bit more complicated. You just have to remember that actually has a direction. So as long as you can account for the direction, you are taking care of a vector. To describe a direction, we have to define a coordinate system. For one-dimensional motion, this is the single axis, like a number line. In general, when describing horizontal motion, motion to the right is usually considered positive, and motion to the left is considered negative. Just like we were talking about in the example with the compass, west direction was negative, east direction was positive. Typically, those are the coordinate systems that we work with. Now, there are special occasions where you can choose which one you want to work with. If you want to make to the left positive and to the right negative, it just kind of depends on the problem at hand. For this figure, it is usually convenient to consider the motion upward as right and to the right as positive, downward and to the left as negative. So now that brings us to time. In physics, we define time as change. We cannot control the flow of time. It is always moving forward at the same rate. But this gives us a great backdrop to measure how things change. Remember that we now have the SI units for time, so the second calibrated very well to the using radioactive decay. Almost all of your physical quantities are measured as a change over time. So for delta t, triangle t is elapsed time. It's calculated as the difference between the beginning of time and the ending of time, just like a displacement, but now we're dealing with time. So we have time final minus time initial. So that brings us to velocity. Your average velocity is displacement, which is your change in position, divided by the change in time, time travel. So here we have V with the line above, which is the for average, equals your delta x, change in displacement, change in position, over your delta t. And that gives you these equations, the ones that we just went over. It's easily to substitute the ones that we know that are equal to those delta x and delta t. So we know that delta x is x final minus x initial, and delta t is t final minus t initial. Notice that this definition indicates that vector is a vector because displacement is a vector. It has both a magnitude and a direction. So velocity is a vector. Okay, so for this figure here, now we're going back to the figure where we figured out where our passenger ended up, but now we're incorporating time. Now we're asking if the time it took for him to walk to the back of the plane was 5 seconds, what was his velocity? So we know our displacement. We know that 2 meters minus 6 meters was negative 4 meters. Now we're dealing with time. So we can say that the moment that he started moving, we'll call that time 0. That's our initial time. And the point where he got to his final position, his 2 meter mark, was 5 seconds. That's how long it took to get to that position. So we'll say 5 seconds minus 0 seconds. So the total time was 5 seconds. So that'll give us negative 4 meters over 5 seconds, which equals negative 0.8 meters per second. Now the units here come from your position on top and your seconds at the bottom. Those SI units are important because if we need to convert them to something else, we need to know exactly what we have. So like if we were asking for kilometers an hour, well, we have to make sure that all of our SI units were right to begin with. So here's a more detailed record of the airplane passenger heading toward the back of the airplane, showing smaller segments of his trip. The smaller the time intervals or measurements, the more detailed the information we have. So for delta A here, he went just this distance. Let's say for delta B, he went a little further. But for delta C, XC, he went backwards for a little bit. And then for delta XD, he went the rest of his trip. So you see how for displacement, we're really only worried about from initial to final. But let's say we were talking about his distance. Well, it would matter if he traveled to the left and then traveled to the right and then came back towards the left. That would matter. But with displacement, we're really only worried about the initial and the final. Okay, so speed versus velocity. In the everyday world, most people probably think of speed and velocity as being the same thing, but in physics, they are different concepts. Specifically, speed is a scalar quantity. Speed has no direction. So speed is just the magnitude of velocity, similarly to distance being the magnitude of displacement. So average speed can be calculated as the distance traveled, also a scalar, over a period of time. So now we dive into instantaneous velocity and speed. So instantaneous velocity is the velocity of an object over an infinitely small interval of time. Basically, it is the velocity at that one exact moment. Same thing goes for speed. So for our understanding, whenever we're looking at a speedometer in our cars, what is that measuring? Speed, velocity. So for here we have A, B, C, D, our average velocity, average speed. Well, average means over an interval of time. So if we were trying to figure out if, what our velocity or speed were from, if we went from our houses to a corner store, then yes, that would matter. But whenever we're we're dealing with just the speedometer, we're worried about just at that one point. If you are driving down the freeway and you're making sure you're going under the speed limit, you will check your speedometer just at that moment. But at the same time, we're only dealing with speed here because our speedometer only gives us a scalar value. It doesn't gives us a negative value. That's what velocity would come in. But we know if we're taking a car in reverse, we're not going to get a negative 5 miles an hour or negative 10 miles an hour. It'll just be whatever the speedometer tells us. So the speedometer only gives us an instantaneous speed here. For figure 2.10, during a 30-minute round trip to the store, the total distance traveled is 6 kilometers. So from the home to the store and from the store to the home, we have 3 kilometers to the store, 3 kilometers to our home. The average speed is 12 kilometers an hour. The displacement for the round trip is 0 since there was no change in position. Now, if I was asking, what is the displacement from home to store, then yes, the displacement would be 3 kilometers. But we're talking about a round trip. If it's a round trip, we're going back to our initial position. So that means that our initial was 0 and our final was 0 because we didn't account for anything in between. So our displacement is 0. So since our displacement is 0, that means our average velocity is 0. Remember, because velocity deals with displacement, not distance. Speed deals with distance. So our displacement is 0 and our average velocity here is 0 as well. So a little bit more of a breakdown to it. Position versus time, velocity versus time, speed versus time for the trip. Note that the velocity for the return is negative. So for this first graph, we know that from 0 to 0.25, that's how many, this is in hours and this is in position. This is about how far we went, right? We went the 6 kilometers and then we came back this way. So for velocity here, it ends up being negative again because we're going backwards. We're going back to where we originated. So the total velocity over time would be 0, but in segments, we can see the difference here. And then the speed, we were told that the average speed around this round trip was 12 kilometers. Okay, so we dealt with displacement, we dealt with velocity. Now we have to deal with acceleration. Acceleration is, think of the gas pedal in your car. The actual name of the pedal is the accelerator. What does it actually do? When you press down on the accelerator, what happens? You accelerate. You speed up. So it is the change in velocity over time. So whenever you hit your gas pedal, you speed up over a certain time. As long as you are pressing down on the gas pedal, you are still speeding up until you decide otherwise. So for here, it's the change in velocity over time, like we mentioned. So we can define your average acceleration as your delta V over your change in time, delta T. But we also have equations for this. So we have your final velocity minus your initial velocity over your change in time, of course. Because acceleration is velocity, which is meters per second, divided by another second, the SI units for acceleration are meters per second squared. So, which literally means by how many meters per second the velocity changes every second. That's a little bit confusing as far as the words, but what you do have to worry about is the SI units for acceleration, meters over second squared. Whenever you're dealing with acceleration, those are the units that you're typically going to work with. Now, yes, you can have different units here and there, but the time on the bottom will always be squared when you're dealing with acceleration. When you're dealing with velocity, the time, whatever units you're working with, hours, minutes, seconds, it'll just be that one SI unit. Okay, so direction of acceleration. Notice that this definition indicates that acceleration is a vector because velocity is a vector because displacement is a vector. We're still dealing with a vector here. They have both your magnitude and a direction. Acceleration is a vector in the same direction as a change in velocity. Since velocity is a vector, it can change either in magnitude or in direction. Acceleration is therefore a change in either speed or direction or both. Keep in mind that although acceleration is in the direction of the change in velocity, it is not always the direction of motion. When an object slows down, its acceleration is the opposite direction of its motion. This is known as deceleration. that can get kind of confusing. Basically, what we're trying to say is, even though, let's say you like this example that they're talking about, let's say you're driving and you're decelerating. While yes, your velocity is still in the positive direction because you're still going in the same direction in the car, your acceleration is in the negative direction because you're actually slowing down. Your initial velocity, let's say you're going 60 miles an hour, and your final velocity, you're going at 30 miles an hour. So here you have 30 minus 60. So that'll give you a negative 30. Your acceleration would be negative here, even though your velocity is still in the same direction. So for A, B, C, D, we have this car is speeding up as it's moving towards the right. It is therefore a positive acceleration in our coordinate system because it is speeding up. You are accelerating. This car for B is slowing down as it moves towards the right. Therefore, it has a negative acceleration in our coordinate system because it is accelerating it's towards the left. You see the arrow here for acceleration is towards the left because it is slowing down. The car is also decelerating. The direction of its acceleration is opposite to its motion. So, like I mentioned, even though your velocity is still to the right here, you are going in the left to the negative direction as from your acceleration. Okay, for C, this car is moving towards the left. So we have our velocity here for C pointing towards the left, but it is slowing down. So our acceleration again is towards the right in the opposite direction. And for D, the car is speeding up and moving towards the left. So we have both velocity and acceleration vectors pointing towards the left. Okay, so for example, 2.1, a racehorse coming out of the gate accelerates from rest, so zero velocity, to 15 meters per second due west in 1.8 seconds. What is the average acceleration? So we go to the problem here. So we are asking for acceleration here, right? And we just discussed that this is the equation for acceleration. So based off the problem, we have from rest, so we know our initial velocity here is 0 to about 15 meters per second. So that's our final velocity due west. That's important because we have to get down a direction. And in about 1.8 seconds. So here is our time. And we're looking for average acceleration. So as I mentioned, we have 15, but remember he's going west. So you have to tack on a negative here. It's going west in the negative direction. And we know we started off at 0. So negative 15 minus 0. Anything minus 0 gives you that same number. So we have negative 15 on top. And we know our time. It took 1.8 seconds to get to this velocity. Now remember, time at the beginning is 0. So we have 1.8 minus 0, which is just 1.8. So you plug that into a calculator and you get negative 8.33 meters per second squared. Remember, you have meters per second on top and you're dividing by another second, so you bring over that squared with you. And with most problems throughout this course, you have to make sure that the answers do make some type of sense. Now, let's say you're solving this and you forget the negative. Would it make sense for us to have an acceleration in the positive direction where we know we're accelerating in the negative direction? It wouldn't. So we have to make sure that in some way, form, or fashion, our answers do make sense while we're solving them. Okay, so models and assumptions. For physics, it can be complicated, and we all know that. There are lots of factors to take into account in real world situations. Therefore, we usually employ a model where we can take certain assumptions in order to make our lives and calculations much easier. Be careful though, your assumptions must always be reasonable in the situation. So for simplifying equations, we can simply simplify definitions for displacement, velocity, and acceleration. But can we combine these somehow? Actually, we can. Let's make some reasonable assumptions to make the equations a little bit easier. So first, assume that any measurement you take starts with time is equaling 0, which this is a fair assumption because there's no way of knowing anything that happened before the starting point. Why would we have a negative time? That really wouldn't make sense. Time is a scalar, so there's no point in us actually having a negative time from the very beginning. So taking your time initially to equal 0 is perfectly fine. So for all these equations, we're going to have just time final or just time. So for here, we have your constant acceleration. While acceleration can increase and decrease based on the situation, this becomes very difficult to calculate. Therefore, we usually try to assume that acceleration is constant. We don't do like acceleration final and acceleration initial in this course. They do exist at some point, but not here. We're gonna make our lives a little bit easier. So under those conditions of constant acceleration and using our newer, simpler symbols, we can define the following equations. Now, these equations here, you can find them in the book, 2.5 to 2.54. And these are pretty much the equations you will be using throughout this chapter and the rest of the course in some way, form, or fashion. So for the first one, if you're looking for that should really be like x final. Your x equals x initial plus your average velocity times time. The second one is velocity, your average velocity equals your v um, not v initial plus that should be really be v final over 2. Your v final for the third one equals v initial plus your at, your acceleration times time. For your fourth one, x equals x naught, your initial x, plus v naught, initial v, times your time, plus 1/2 at squared. That's the one that gives a lot of people some issues, and later on we'll know exactly why. It gets a little bit complicated just because of that t squared at the very end. And the last one is v final squared equals v initial squared plus 2a. So this one, the x minus x final, you could really call it just delta x because it's change in x. That's one of our first equations that we talked about. So get familiar with these 5 equations. Make sure you know how to use them and what situations to use them, and just try to practice them as much as you can. Okay. So for example 2.8, we have a jogger runs down a straight stretch of road with an average velocity of 4 meters per second for about 2 minutes. What is the final position taking his initial position to be 0? Okay, so that helps us a lot because now we know his initial position. All right. So here we want a final position. And like I mentioned, those equations that should really have your x final, your v final. That way it's a little bit easier for people to use. But we know we have to use x equals x naught plus vt. It kind of has everything that we need. We know our velocity, which is 4 meters per second. We do know our time, which was 2 minutes. We know our initial x because they told us to assume that it is 0. And we are looking for our x final. So for here, we write down everything that we do know. And one of the things that they did subtly here, they changed those 2 minutes to 120 seconds. Okay. They changed it because our velocity here is in seconds. There's no way of us getting rid of this SI unit here for seconds while having minutes. So always try to keep your SI units the same throughout. If you're working with time, make sure that they're always in seconds, minutes, hours, whatever the case may be. Same thing for distance. So that was one of those things that they just did subtly. So we're gonna enter everything into this equation. We have x equals x naught plus vt, which equals 0 because our initial x was 0, plus your velocity, which was 4 meters per second, times the 120 seconds, which is equivalent to 2 minutes. You multiply that together and you get 480 meters. So that's how far he went. So for this next example, we have an airplane lands with an initial velocity of 70 meters per second and then decelerates at 1.5 meters per second squared for about 40 seconds. What is the final velocity? Okay, so kind of the same situation like we just did, but now we're talking about acceleration and velocity here. Okay, so identify what you know. You know that your initial velocity here, 70 meters per second. We know our A is negative 1.5 meters per second squared because they did mention it's decelerating. If it's decelerating, like I mentioned before when we were talking about the direction of acceleration with the car, you do have to know where everything is accelerating in the positive direction or decelerating in the negative direction. And we know our time, 40 meters or 40 seconds that it took for all this to happen. So going back to those equations that we were talking about, we know that we're looking for our V final, which equals your V initial plus AT. So our V initial here velocity that it was going in before it started decelerating was 70 meters per second. Plus, we know that our A is negative 1.5 meters per second squared. And we know that our time was 40 seconds. So here, all of our SI units match. Once we multiply these two together, one of these seconds will go away because you're multiplying a second and dividing by second squared. One of those cancels automatically. So you'll be dealing with meters per second plus meters per second. You can't add or subtract anything that has different units. It's like those sayings, you can't add apples and bananas. It's not the same thing. So you have to make sure all your SI units are the same here. So once we do all this through, we get 10 meters per second. That's our final velocity once the deceleration is done. So for example 2.10, so we have dragsters can achieve average accelerations of 26 meters per second squared. Suppose such a dragster accelerates from rest, so 0, at this rate for 5.5 seconds. How far does it travel in this time? All right. Okay, so identify what you know again. We have our acceleration in the positive direction here as 26 meters per second squared. We know that it's starts from rest, so we know that our initial velocity is 0, and we know our time as well, 5.56 seconds. We want to know how far it goes. So here we have this equation, x final, we want to know how far it goes, equals our initial x, which we know it starts at 0 because it starts from rest. It's one of those assumptions we were talking about. Plus our initial velocity, which is initial velocity was 0 because it was at rest. We know our time, we're trying to figure out at 5.56 seconds how far it went. So plus the 1/2, just bring it on with it, times our acceleration, 26 meters per second, times our time again, 5.56 seconds. So x initial is 0, don't have to write that down here. So we have our v initial here, it starts at 0, it starts at rest, so we know that that is 0. So all that's left is the 1/2 AT squared here. You plug everything in, everything has the right SI units here, and we are left with our distance being 402 meters. That's how far it goes in 5.56 seconds. Okay. So here, a manned rocket accelerates at a rate of 20 meters per second squared during a launch. How long does it take for the rocket to reach velocity of 400 meters? So So this one's actually in the textbook as well. It's just well below all these examples here. And these examples are actually pretty great. This is one of the reasons why I was saying the long equation, this one here, gives a lot of people a lot of headaches. Because if you're trying to solve for time and you have to use this equation, which is very common, you have to use this equation here, the quadratic formula. And this is just a given mathematical formula. Uh, so from here, you plug in everything that you basically know. And I'm not going to cover this in the lecture. There are a few examples here that cover it as well. And everything kind of spits it out. Here you have like your equation here. You have t squared plus t or 10t minus 200. So it resembles this equation here, which turns into this one here. Like I said, this is just a given mathematical formula. So if you have your a, b, and c, you can plug in your a, b, and c to this one, this equation here, and then just plug it into a calculator, and it'll give you actually two solutions. One will more than likely be positive, one will more than likely be negative. And with time, obviously, you can't have a negative time. So I always try to take the one that makes the most sense. But like I said, we're not going to cover it in the lecture. It is just something that gives a lot of people a lot of headaches with. Uh, oh, it was right here. So this one is actually not an example given in the textbook, but it's a check on your understanding. So over here we have your v final. That's what we're trying to find. How long? Actually, we know our v final. We have 400 meters a second. We know our initial velocity was 0 because it started at 0. We have an acceleration of 20 meters per second, but we are trying to find our time. So for this check your understanding here, we have to rearrange this formula here to make it equal to time. And that's how we are able to find this answer. So this is simple. We have our velocity here, and we want to isolate our t like they have it here. So we are going to subtract our v initial first. That'll gives us your v final, and they didn't label them here correctly. This should be your v final minus your v initial, right? And all that is left on the right side is at. These two are being multiplied, so we must divide them. So you divide it by your a, and that'll give you t equal to your v final minus your v initial over acceleration. But now it is this equals what you are looking for. So you plug in what you know. You have 400 meters a second, which is the final velocity you're trying to reach, minus your initial velocity, which is 0 because it started at 0, divided by your acceleration, which is 20 meters per second. And that gives you 20 seconds. That's how long it takes for it to reach that velocity, which is actually not that long at all. Okay, so for problem solving skills for these types of problems here, we want to examine the situation to determine which physical principles are involved. It often helps us to draw a simple sketch and at the outset. So basically, if you've noticed with all these examples, they've had some type of sketch, they've had some type of diagram showing exactly what is going on, and it makes it easier for everybody to know where this the problem was going. So if we know we're going, 20 meters to the right and then 10 meters to the left, sometimes it's easier for us just to visualize it. So that way we know, okay, well, we don't have to keep that in the back of our minds and try to solve this problem. Now that brings me to another point. With everything that this course brings, you must show your work with everything, even though sometimes it's kind of given, like a certain problem. Let's say it starts at 0. You must say that, okay, well, this is starts at 0 or whatever. Something that symbolizes pretty much your train of thought, and that's where this comes from. If you draw a sketch, then I know exactly what you were thinking at that moment. For step 2, make a list of what is given and can be inferred from the problem as stated. And you've noticed on all of these examples so far, it was always identify what you know, identify what the problem is giving you. If your velocity is, like this last example, if it reaches 400 meters per second, that's something that you know, that's something that you must write down. If it starts at breast, if it starts from an initial position at 0, then you know that your initial x and your initial velocity are 0. For step 3, identify exactly what needs to be determined in the problem. So figure out what you're looking for. Figure out if you're looking for time, for acceleration, for displacement, for velocity, just whatever the end game is for that particular problem. For step 4, find an equation. So from those equations that we talked about and going forward from any equations that are given, always look at the equation list. Always look at exactly what you can and can't be using. Obviously, for like let's say for these beginning problems, you can't use something that you're being taught in chapter 9 or chapter 10. You have to kind of stick to what is being used. For 5, substitute the knowns along with their units. So pretty much plug in the numbers that you do know, plug in everything that you are giving in that problems, and make sure that all the numerical solutions complete with the units. You have to make sure that all your units are in the right units. You can't have seconds and minutes like I mentioned earlier. In step 6, make sure it makes sense. I mean, if you have a negative time, or if you get a negative acceleration, but you know that the problem is calling for accelerating, make sure just that your answer makes some sense. Okay, so that brings us to falling objects and gravity. The most remarkable and unexpected fact about falling objects is that if air resistance and friction are negligible, then in a given location, all objects fall towards the center of the Earth with the same constant acceleration, independent of their mass. So we do know that in real life, we can't neglect air resistance and friction, but for this topic here, we're going to say that we are. So we know that in air, a hammer would fall much faster than a feather. But if we ignore air resistance and friction, we can say that, okay, well, they fall at the same time. That's what this diagram represents. So in the real world, air resistance can cause a lighter object to fall slower than the heavier object at the same size. An index card will reach the ground after a hard baseball dropped at the same time. For ideal situations of these for the first few chapters, an object falling without air resistance or friction is defined to be in free fall. The force of gravity causes objects to fall towards the center of the Earth. The acceleration of free falling objects is therefore called the acceleration due to gravity. The acceleration due to gravity is constant, because that's what we're going to say. They are actually some points of the Earth where gravity is different than other points, but we're just going to leave that there, which means that we can apply the kinematic equations to any falling object where air resistance and friction are negligible. And it's just something that we are just going to take for in this chapter here. So here are our free fall equations. As you can kind of tell, they are very similar to the other equations we talked about. The only differences here is that for our position, here we're talking about the y direction. Remember, it's going up and down. Our axis going up and down is our y-axis. So that's why we substituted the y instead of the x, but it still means displacement. It still means your distance. And our gravity here, you see that g, that's for gravity. Our acceleration due to gravity, as mentioned here, is 9.8 meters per second squared. So all we're doing is substituting the g for the a, but it's still your acceleration due to gravity. So here, example 2.14, a person standing on the edge of a high cliff throws a rock straight up with an initial velocity of 13 meters per second. The rock misses the edge of the cliff as it falls back to Earth. Calculate the position and the velocity of the rock at 1 second, 2 seconds, 3 seconds after it is thrown, neglecting the effects of air resistance. Okay, so like we said before, identify what you do know. Remember, we're talking about our y-axis. We're talking about going up and down. So here we know that we start off at y equals 0. That's our starting point here. But we also know that in the problem that tells us that the initial velocity was 13 meters a second. So we have that. We know that acceleration is our acceleration due to gravity, which is also 9.8 meters per second squared. And we know that our time is 1 second. Now, what you will notice is that there is a negative here in front of our 9.8 meters per second squared. If something is working against gravity, which means it's going upward, you're going to have a negative gravity, a negative in negative 9.8. Now, if it's working with gravity towards the center of the Earth, you'll have a positive 9.8. That's where you knowing a vector has a direction comes very handy here. So we want to know where it is after 1 second, after 2 seconds, and after 3 seconds. So here you just simply plug in all your numbers with this equation here, y equals y naught plus v naught t plus 1/2 at squared. We know that initially it is at 0. We know our initial velocity. We know our second plus 1/2 negative 9.8 because it's going against gravity. And our second again squared. That gives us 8.1 meters. So that's after 1 second, that is where this object is. Here we have our V1 is equal to V final or V initial minus GT. So this is finding our first velocity here after 1 second. And we're using this equation because we know our initial velocity, which is 13. We know our gravity here, and we also know our time, right? So plugging all this in, we know that it's 3.28 meters per second here. All right, and here we, instead of putting a plus negative 9.8, all they did was just subtract it because we know that a negative times a positive is going to give a negative. So we know that this negative here can just be, taken out and substituted for a subtraction sign. So if you keep doing this for 2 seconds and 3 seconds, so on, you'll get that our position here, our velocity here, and our acceleration. But our acceleration, as you can tell, doesn't change. Our position does every second, and our velocity does, but it doesn't change for our acceleration. But here, what you can tell, at 1 second it was at 8, but at 2 seconds it was at 6. So it's probable that after 2 seconds it was already coming back down to Earth because this position is lower. And at 3 seconds it was in the negative, so that means it was already past the cliff. It was already on the way down. We were looking down at that rock falling towards the Earth. Same thing with our velocity. We know that it was at 3.2 after 1 second, but we were going against our initial direction here. So we know that it was definitely falling towards the Earth after 2 seconds and farther after 3 seconds because of these negatives here. Now, if they were still positive, if this was a positive 6.6, that means from position 1 to position 2, it actually increased. But because of this negative, we know that we're working against the initial direction that we called for. Okay. Going back to the PowerPoint here. So for here, our vertical position, vertical velocity, and vertical acceleration versus time for a rock thrown vertically up at the edge of the cliff. So it's pretty much representing the example that we just did. Notice that the velocity changes linearly with time, and the acceleration is constant, which is what we just saw in those graphs, which are here actually. So misconception alert, notice that the position versus time graph shows a vertical position only. It is easy to get the impression that the graph shows the horizontal position. So they're talking about this first graph right here. We're only discussing the position in the y direction, in the vertical position here. Even though, yes, this graph shows an y direction and an x direction, you have to realize our x direction here is in time. We have a graph doing position versus time. This isn't a graph that is going in your x coordinate and your y coordinate. We're dealing with position versus time here. So for here, like I mentioned, after 1 second, it was still going up. And between 1 and 2 seconds, it started going back down. And after 3 seconds, it was well on its way down. So this is where it started. Let's say that this is the cliff. And after 3 seconds, we were already looking down at the rock going down. Same thing with our velocity. It started here initially, it started decreasing, decreasing, decreasing until here it reached zero. If you look at these two graphs, about the same time the velocity reached zero, the rock stopped going upwards. So at that instantaneous position, the rock was stopped. It was at zero. Velocity was zero. And then it started going back down. So our velocity increased in the negative direction here because the rock was going down in the negative direction. And like I mentioned, velocity just started, just kept at 9.8. Okay. So graphical analysis. Graphs not only contain numerical information, they also reveal relationships between physical quantities. We can use graphs of displacement, velocity, and acceleration versus time to illustrate one-dimensional kinematics. When two physical quantities are plotted against one another in a perpendicular graph, the horizontal axis is usually considered to be an independent variable, and the vertical axis is the dependent variable. If we call the horizontal axis the x-axis and the vertical axis the y-axis, there is a straight line that also has this form, which is y equals mx plus b, where m is your slope, defined to be the rise divide between or by the run. So rise divided by run, y over x. The letter b is used for the y-intercept, which is the point at which the line crosses in the vertical axis. So this is a representation of that. Like we mentioned, your b is the intercept between the y-axis here, where it crosses over, and your m, your slope, is your change in y over your change in x. So the change in y in the y-axis versus your change in x in the x-axis. Okay, so graph of displacement versus time for a jet-powered car on the Vaughnville salt flats. We typically use time as an independent variable since we have no control over it. So time, for the most part, will have to be on the x-axis because it is independent. We do not have any control of time. While your displacement, your velocity, and your acceleration will have to be on the y-axis here. And as you can see, for this figure here, we have our displacement versus our time. So displacement is in the y-axis, time is in the x-axis. But our slope here, because we said it was delta y over delta x as a general form, here we have delta x, which is our y-axis, over our delta t, which is our x-axis. But our slope here is actually equal to our velocity because that is what delta x over delta t is, right? So going forward, same thing goes for acceleration here, or for your velocity. Your slope here would be your acceleration. And acceleration has one as well, but we won't get into that in this course here. So for A, which is our displacement versus time, the slope of a x versus t graph is velocity, like I mentioned. This is shown at 2 points, and the instantaneous velocities obtained are plotted in the next graph, which is this next graph here. Instantaneous velocity at any point of the slope of the tangent at that point. So for B, the slope of the v versus t is constant for this part of the motion, indicating a constant acceleration. So for here we have P and Q. While our positions does change kind of in a quadratic form, our velocity is just linear. But because our velocity is linear, that means we're not accelerating. Acceleration is not doing anything. So our acceleration is actually constant here. Okay, and that's what this graph down here represents. So for figure 2.52, a graph of velocity versus time of a ship coming into the harbor is shown. So describe the motion of this. So we know that it is at a constant velocity here. Let's call this just v initial. If you want to give it a numerical value, you're more than welcome to. We can say 10, going at 10 meters per second. But then it decreases. Let's call this about 2 meters a second over time. So it actually decelerates here, right? Because our velocity is slowing down. then it decelerates a little bit more here until our velocity is 0. So we had a constant velocity here, decelerated here, so our velocity was going in the negative direction, and then same thing here, but this was over a different period of time and at a different decelerating. But if we put that in graph form, this is what it would look like. For this segment here, we weren't accelerating, we weren't decelerating, nothing was going on. For this portion here, we were decelerating at a constant rate, so that's why it's in a horizontal version here, but just the magnitude of A was a little bit greater here. And then for this portion here, we were decelerating as well, but at a slower rate here. So we can say like it was decelerating at like -1 meters per second squared, and we can say this is -2 meters per second squared. But the point is to know exactly what each segment between the velocity versus t and your acceleration versus t, where they would fall under. Okay, so for, like I said, for this chapter here, make sure you focus on every single topic. This is one of those top chapters where everything that is covered is very important. Chapter 3 coming up is actually over two-dimensional kinematics, which will pretty much just enhance here what this chapter went over. So make sure you understand everything that this chapter brings, and if you have any questions, please contact me.